In statics and mechanics in general, a very convenient way to mathematically describe a lot of the physical quantities we're going to be talking about is with vectors. And a vector is a quantity that has both a magnitude and a direction. Now, this is different than a scalar, which is what you're probably most familiar with. A scalar only has a magnitude, so a scalar is just a number. Some examples of scalars are maybe 2, a 5, a -1. It can be anything, but it's only a number, -1,000. And a vector is going to have this magnitude, so it's going to have a number, say 2, and it's going to have a direction. It's maybe pointing straight to the right. So this is a vector, this is a scalar. They're very different, and it's important to distinguish between them. And books go out of their way to distinguish between them by denoting vectors differently. Different books you look at, maybe they show it in a different way, but common ways are sort of, if we have a vector v, maybe it has an arrow over, or a half arrow over the v. Maybe it has a half arrow or an arrow under the v. Maybe it's bold-faced. So books are going to go out of their way to distinguish between a vector and a scalar, because as we get into more complicated examples rather than just what is a vector, it's very important to distinguish between these two. Now, graphically, we're going to draw vectors as arrows. And if we draw an arrow sort of like this, an arbitrary arrow, we're going to define some features of this arrow. This tip of the arrow, I'm going to mostly refer to as the head. And this side of the arrow, I'm going to refer to as the tail. It might be called other things in different books, but this is the terminology that I'm going to try to adhere to. Now, the direction that this arrow points, this line it's pointing towards, is called the line of action. And the line of action is some angle from the horizontal. So this is just some angle theta. And this angle theta is the angle that our vector is located at. So here's its direction. Its direction is along theta. And its magnitude is the length of this vector. So my hope in this video is to go through scalar multiplication, vector addition, vector subtraction, and how to resolve vectors. And the first thing I'm going to talk about is scalar multiplication. And as its name implies, it's multiplying a scalar with a vector. So if we have a vector u right here, and this is a vector because I'm denoting it with an arrow over its over the variable. It's really 1 times u, and I'm going to say it's just pointed towards the right. And let's say I want to multiply this by 2. So actually, let me draw it right here. So here's my vector u. It's pointed totally towards the right, and I'm going to multiply it with the scalar 2. Now, when I do this, my vector u just changes its length and becomes twice as long now. And this is my new vector 2u. So by scalar multiplication, we're going to be changing the effective length of the vector. We can make it bigger by multiplying by a number that's greater than 1. We can keep it the same size if we multiply by 1, and we can make it smaller if we multiply by a number that is less than 1. So if we multiply by, let's say by 1/2, and we go 1/2 times u, and again, here's my vector u. this 1/2 is going to shrink it to 1/2 of its length. So my new vector is going to be, somewhere around here, just by eyeballing it. So this is going to be 1/2 u. The other thing we can do, we can change the direction of the vector. So if we multiply by a negative number, we're going to flip the vector. If I have u, I don't know why I like u, and here is u. And I want to multiply by a -1, so -1 times u. I just flip it. So it's now, instead of going towards the right, it's going to be going towards the left. So it's just flipping the vector. Okay, so that's scalar multiplication, and it's changing the effective length or direction of the vector. Vector addition. Now let's say I have two different vectors. If I have u, and I want to add it to a vector v. And let's use different colors here. So v will be red. And let's say u is this long vector like this, and v is a shorter vector that is straight to the right. Sort of down, I guess. It'll make for a better example. So if I have u plus v, I'm going to add vectors tail to head, tail to head. So what that means is I start at some point, and this is going to be my origin, and I'm going to add vector u. And it looks sort of like this. Tail to head. Now I'm going to add in my vector v, and I go from tail to head. And my resultant vector r is going to be this yellow line, and we'll call this yellow line r. So r is going to be equal to my vector u plus my vector v. And I can get this two different ways. I can get this by adding u plus v, and I can also get this by adding v plus u. So if I start at the same point right here that I started at u, and I go down with v instead, and then I add u to it, I'm going to end up at the same place. So this shows that vectors, when you add them, vector addition is commutative. It doesn't matter the order that we're adding them. And this is also equal to v plus u. And when we're analyzing vectors, this sort of parallelogram is very important. We're going to use this parallelogram law a lot. If we know that this side is going to be equal to this side v is going to be equal to this side v. So we can figure out a lot of these angles in here just by simple trigonometry. Law of cosine, law of sine. So we've talked about scalar multiplication, vector addition. Now let's talk about vector subtraction. If let's have two vectors. Let's call them a this time and b. And I want to subtract a and b from each other. If I have a, we'll say it's up like this. We'll say b is going to be to the right. And I want to figure out what A minus B is. Notice this minus sign is effectively multiplying this vector by a minus 1. So we have a minus 1 right here. So this is going to be A plus a minus B. So if we go A and we add a minus B just means it's going this way. So this is minus B, this is B, this is A, and this is A. We're going to have an A minus, and our resultant is going to be this arrow. Here's our resultant. So what we have right here is sort of a special case of addition. It's really, we could say it's this A plus a minus B vector. So here's scalar multiplication plus here's vector addition. So now let's talk about how to resolve vectors. And by resolving vectors, I mean if we're given a resultant vector here, so here's our resultant R, how do we decompose this and figure out what our A and our B vectors are? So the first thing we need to know a couple of things. We need to know the line of action that our A and B vectors are on. This is to make this a unique solution because there are an infinite amount of vectors that can add to give this resultant. Just like if I asked you to list all the ways to add numbers up to get 7, you could come up with an infinite amount of combinations to make 7. So if I know the line of action of A is this way, and I know my line of action of B is going to be this way, I can resolve my vectors by first drawing a parallel line to A from this tip of the head of the vector. So I'm going to construct this line right here, and a parallel line of B from the tip of the head of the resultant vector. And when I do this, this is what happens. If using that parallelogram law, we know that green's not the best color. Let's go with red. This is going to be my A vector. And we also know that this right here is my A vector. With my B vector, this is what my V vector is. And this is what my B vector is. So you can see that this parallelogram law, although I didn't draw it perfectly, is very similar, is exactly the same as the parallelogram law that we dealt with when we were adding our vectors together. So again, this is going to be important further on down the road, but this is how we resolve a vector if we're given a resultant and we want to figure out the two vectors that make up the resultant vector.